Hello everyone, this is Greg. How are you doing? It's a nice warm summer day in Oregon, and I don't believe we've done a video yet, so I wanted to just do one and introduce myself a little. I just use my little iPad here and I record from the kitchen table, and sorry if the light's a little odd and that kind of thing, but this process works pretty good. I do a lot of these, so I just wanted to say first of all that I think the course is going pretty well, and I really appreciate all your hard work. We are now in week 5, and so we're working on the central limit theorem, statistical significance, and next week is week 6, so we've got week 6, 7, and 8, and I'm going to be sending out some information, but unfortunately, weeks 6, 7, and 8 are the most challenging for 2 reasons. The material gets a little more complex, but as usual, we'll work through it. And then the second reason is that the final project, you really have to start working on that final project in about week 6, which is Monday, and then have a good solid draft of it within 2 weeks, because it's just too much to do in week 8, and rarely are people successful if they wait to start to week 8. And so we'll set up a process by which you start working on the final project, and then we start to help you and guide you through it so you have a great product when week 8 is here. Okay, so we'll be starting on that Monday morning for sure. So up to this point in the course, the first 3 weeks were a little bit of theory about what's the scientific method and that kind of thing, and then you started doing your descriptive statistics and your mean, median, mode, standard deviation. It's important to understand all of those foundations if you're going to do any data analysis, and quantitative research is a great field. It's in demand. It's something that if you are going to excel in the educational realm, I think you should become quite comfortable with it. So one of the things I wanted to do tonight is just give you a little idea of what the central limit theorem tells us, and do a little graphical picture kind of thing. So let's give that a try. Okay, so I got my high-tech little whiteboard here. And the first thing I'm going to show you is, let's create a hypothesis, and let's say, here it is, that the mean SAT score of seniors in Kentucky is 500, okay, with a standard deviation of 150. Now, so there's our hypothesis. The mean SAT score is 500. Now, you know from the empirical rule, which you studied, that 68% of the values of in any normal distribution are between plus and minus 1 standard deviation. So that would mean 68% of the seniors scored between 350 and 750. And that's what the empirical rule tells us, and that applies to all normal distributions. Now, it's important to understand that the standard deviation and the empirical rule do not apply to distributions that are skewed, okay? And tomorrow morning we're going to have a little information on what would skew a distribution, what would not. So a variable that varies normally, so let's say if you start throwing darts at a dartboard, sometimes you'll be right, sometimes you'll be left. The deviations from the middle would be normally distributed. That's due to random error. When they began to measure the speed of light, of course the speed of light has never changed since the beginning of the universe. They got different measurements, sometimes a little high, sometimes a little low. Those were just random variations. And so a normal distribution of something is usually variable, is usually due to unknown factors or a random distribution. Now, let's say we take the height of 16-year-old boys in an underdeveloped country. They may not be distributed normally. There might be some boys that are extremely tall because they're fed well, or it has something to do with their social situation or economics. So I'm going to talk a little bit about what's a normally distributed variable and what's not tomorrow. Okay, so how do we test our hypothesis? So again, here it is. All right, so you know from the central limit theorem that the mean of all possible sample means is equal to the population mean. So let's say I have down here, the second graph is a histogram of all possible sample means. And the mean of the means is exactly equal to the population mean of 500 in this case. So now, let's say we take a sample, all right? So we take a sample and we get a sample mean of, let's say, 600. Now, there is a sample in there that has a mean of 600. However, there are not that many of them. There are not that many samples that have a mean of 600. So what does this tell us? Well, through a little bit of mathematics in the empirical rule, we can say that if we got a mean of 600 and there are very few sample means of 600 in the distribution of sample means from a population with a mean of 500, then it's probably likely that the actual population mean is not 500. Now, it could be, but it's not likely. And so that's what the central limit theorem helps us do. It helps us to determine whether the mean of a population is what we think or whether it is unlikely. And in this case, because of the empirical rule, you only have a very small chance that you're going to have a sample mean with 600 when the population means 500, so you might reject the null hypothesis, which is that the mean is 500, in favor of the alternative, which is that it's not. And so you're going to see a little more clearly how all of this works next week. So I just wanted to encourage everybody, stay with it. I appreciate the calls, and you can call and text anytime. We want to get all of the week 5 assignments and everything caught up, because week 6, 7, and 8, there's quite a bit of work. And so once again, I appreciate your hard work, and that'll be it for this evening, and I'm enjoying working with you, and everybody have a great evening. Okay, thank you. Bye.